What's going on, guys? Welcome back to another video on a new recommender system paper again, and this one is deep and cross networks for ad click prediction. So this is also one of the most highly cited papers from Google, and they actually have the abbreviation is DCN, and there's actually another one as well from 2020, DCN V2. And we will probably take a look at that one as well in the future. So this is for basically, like ads, where, the most important thing is click-through rate. They are paid through click-through rate. Like they have, I think it's like per impression, how the payment of that works. So click-through rate is really important, but this is usable in recommender systems in general too. But so that's sort of the setting, ad click predictions. So yeah, let's just step through it. This is actually like the ideas underlying these papers are, like, if you really dig into it, it's quite simplistic in nature, but at the same time, there's a lot that goes into it, right? But it's definitely interesting to follow these papers to sort of see the development. So what they say here in the abstract is that feature engineering has been key to the success of many prediction models. Good features are important, and that deep neural networks are able to automatically learn feature interactions, but they generate all the interactions implicitly. So this is generally a good thing. You set up the model so that it learns what's important by its own, but there are ways we can, by knowing the structure of the input, we can guide the model to learn specific things. Like we might know that there are certain type of structure in the data that's more important than others, and sort of giving that to the model very clearly makes it very easy for it to learn, then rather than trying to figure out all of these complex things on its own. All right, so let's keep going. For the introduction, they say here, click-through rate is a large-scale problem that is essential to multi-billion-dollar online advertising industry. This is like, people don't want to talk about these things, and in general, recommender systems are not that popularized in the machine learning community. If you look at research papers and so on, it's actually quite a small percentage compared to computer vision and NLP. But if you look at the actual revenue, recommender systems accounts for, like, I don't remember the percentage, but it's like 80 or 90%. This is what generates money for companies, and it's essentially like this is the building block of everything. Essentially, it's not the most exciting, making these models to be able to click on ads. But I guess there are multiple ways of looking at it as well. I mean, we are improving, we are giving better recommendations of products to buy, but there is more of a philosophical question of, is buying stuff really good for happiness and so on. But yeah, I don't want to get into that too much. Let's just, because also recommender systems can be used for many different types of things, and they're not necessarily only used for ad click-through rate. All right, let's see. So for data for web scale, recommender systems is mostly discrete and categorical. We have a mixture, and this leads to oftentimes very large and sparse feature spaces that is challenging for feature exploration. Another thing is that these recommender systems are very, you require low latency and really fast models with low memory requirements. So this is another thing, is that, we need to really keep in mind. So they say here, cross features, on the other hand, have been, they say here that linear models like logistic regression are very limited, but cross features, on the other hand, have been shown to be significant in improving the model's expressiveness. Unfortunately, it often requires manual feature engineering or exhaustive search to identify such features. Moreover, generalizing to unseen feature interactions is difficult. So yeah, this is feature engineering is still an issue. Even though we just feed it to a neural network, it might not be very clear to it what it's supposed to do. So they, in this paper, they aim to avoid task-specific feature engineering by introducing a novel neural network structure across network that explicitly applies feature crossing in an automatic fashion. So basically, they try to guide the model and show, that in this particular application of click-through rate prediction and so on, cross features are very important, and the neural network might have a difficult time learning that. But if we can guide it to have that structure, we make it easier for the neural network, and yeah, basically it works better. So let's go on, because I think this figure is pretty much the main thing here. But what they do here, the contributions of this paper, is they propose a novel cross network that explicitly applies feature crossing at each layer. This is the guiding of the what's important from what I was mentioning earlier. The cross network is simple yet effective, and it is memory efficient. So, you might ask, or let's go through it first. So basically here, you have x0, which is the input. You have some dense features, yeah, I don't know, like some features, and you also have some sparse features that you send through some embedding layer, and you get an embedding vector. So you get all of those, you concatenate them, right? And then what they do is that they send it through a deep network, and you get some output from that, right? Just normal linear layers with nonlinear activation functions. But then this is the contribution here, is the cross network. So it might be difficult for the neural network to learn the feature interactions. Yeah, I mean, they need to learn the weighting for that, but we know directly maybe that the interactions between the features are extremely important in this case, and that we want to give the model those types of structure in the data. So they do a cross product, right, of x0, this feature vector, which results in a matrix. Showing the feature interactions, or more information about the feature interactions. So we're giving the model the input, sort of these are the feature interactions. Can you take these and compress them with a weighting matrix or a weight? And then they do that for a couple of layers. So what really to me is the essential thing here is that we already know that feature interactions are very important, so we already give that in the input. We already structure it that way. And then it's just a bunch of layers on top of each other, so we can learn, more better representations of the feature interactions. But here they need to learn them. They need to learn not only the feature interactions, but it also needs to learn sort of what feature interactions are important as well. Let me know if you have different thoughts on this, but that's sort of my intuition on why it works. And you could, I thought, well, why not just use a transformer? But this paper is from 2017, and they don't use a transformer here. And also in the DCMV2, they don't use a transformer, which was from 2020. So they definitely know about transformers, right? But I think, the problem of using transformers is computational. Transformers are not memory efficient, I don't believe, in this way. This is very efficient and memory efficient. And so I think learning these feature interactions in a very efficient way is what they really try to aim for here. I think this would be possible to get the same type of result with a transformer, but you would have higher computational costs probably. So those are some of my thoughts on this. And then they just stack this and they predict single output. So I mean, this is like click-through rate or something. So yeah, that's pretty much the architecture. What they go through here as well is so this is the formula. They take this cross product of the previous layer, and actually they do. Okay, I didn't see that earlier. Yeah, so they take x0 of every step, but xl from the previous input. So that's yeah, I guess that makes sense. And then you take the WL plus BL plus the previous layer. All right. So basically they do the same type of formula here as they did here, except that it's always multiplied with x0 here, and this is the XL, the layer sort of previous. So that's the formula for that. The key here is the high degree interaction across features. You know, we send in the structure, and so it learns. It can more easily learn interaction. You know, basically they go on to say here, you know, it's very it's linear in input dimension, so it's very efficient. And yeah, so here this is an analysis they have where they try to, from sort of a more of a mathematical perspective, try to explain why this is so effective. And I don't know, I don't think this is too important for us. I feel like this is yeah, it's difficult to know. They even have three different sort of explanations here. So one is polynomial approximation. But I don't think we need to go through this too much. It's not too important, but you can read it if it would be interesting. Then they basically compare the model performance. So they check, you know, compared to previous ones, and they use log loss as the metric. Now here, log loss, like it's very small differences, but the small differences are actually significant. And yeah, basically, you know, DCM performed the best here, and compared to factorization machine-based models, linear regression, and sort of only using a deep neural network. And they also performed really well with a low memory budget. And they also checked on non-CTR data sets to show that this type of network is not like only for click-through rate prediction problems. It also generalizes. So the conclusion, you know, here is that identifying effective feature interactions has been key to the success of many prediction models. Regrettably, the process often requires manual feature crafting and exhaustive searching. Deep neural networks are popular for automatic feature learning. However, the features learned are implicit and highly nonlinear, and let's see, unnecessarily large and inefficient in learning certain features. And I think this has to do with the problem we're asking it to solve. When we're giving it the structure this way, we are sort of telling it more, we're sort of guiding it, is how I view it. So we make it a bit easier for it to know what's important to focus on. The deep and cross networks proposed in this paper can handle a large set of sparse and dense features and learns explicit cross features. Yeah, and then our experimental results have demonstrated its superiority over state-of-the-art algorithms on both sparse and dense data sets in terms of both model accuracy and memory usage. All right, so that was DCN. What was it? Deep and cross networks for, let me go to the top here. Deep and cross networks for ad click predictions by Google in 2017. There's a DCM v2 in 2020. We'll go through that one probably. Let's see. I don't know if it will be next though. All right. Hopefully that was 15 minutes. Pretty compact summary of this paper. Yeah. Let me know if you have any questions, and hope you have a good day, man.